All right, so here's the second example. It's going to involve some string and a standing wave on the string. And I chose one to bring in some ideas about the tension and the linear mass density. So you can see how it's all kind of mixed in together that way. So the scenario that we're going to deal with is we're going to have a piece of string. Oops, wrong lever. It's clamped over here. It's going to go over a pulley, come down, nice and straight-ish, and we're going to have a mass down here. So I'm going to call this M1, and the mass is going to be 200 grams. Okay, now let's get some dimensions going on here. All right, so from here to here is 1.5 meters. And down this way is a 0.5 meter. Okay, so the total amount of string we've got is 2 meters. Okay, 2 meters of string, and that 2 meters of string has a mass, let's say, of 0.005 kilograms, so 5 grams. All right, so string's pretty light, doesn't weigh very much, of course. All right, now what I want to know is if this thing is going to oscillate in the third mode, which is going to look like this, okay, what frequency will we need to produce? Okay, so if we wanted to move like that, what are we going to have to do there? Okay, so one of the things that we saw in the last video is that this relationship here is a great place to start. Lambda F is V. Okay, these are discrete values, so we could put little n's on here. There can only be certain lambdas and certain frequencies, sort of like that. And that then is going to tell us that F3 has to be V over lambda 3. All right, just like that. So what we have to find now, we have to find the velocity, so it doesn't tell us the velocity, and we have to find the wavelength. Okay, so let's start with finding the wavelength. Okay, so we have symmetric endpoints, and then so the relationship is very simple between the wavelength and the total length. It just goes a certain number of half wavelengths. Okay, so in our case, n equals 3. So that means we have L is 3, lambda 3, over 2, which tells us that lambda 3 has to be 2/3 of L. So that's 2/3 times 1.5 meters. And therefore, lambda 3 is 1 meter. Just like so. Okay. And it looks like I'm being a little fast and loose with my sig figs there, so I hope you'll forgive me on that. On a test or something, I'll make sure all the numbers sort of match that way. All right. So we've got the wavelength. We still need the velocity. Okay. So we got to roll back in our head and we'll be able to be like, oh, speed on a string, wave speed on a string. And the wave speed on a string is V is the square root of the tension divided by mu. Okay. So our tension, all right, we got to realize we've got the weight of our mass pulling down. W1. So the tension then is just W1, which is M1G. And in this particular case, that turns out to be 1.962 newtons. Okay. Now, mu is going to be the length of the mass of the string divided by the length of this string. All right, so we're looking at 0.005 kilograms divided by the length of the string, which it's 1.5 across and then it's 0.5 down. So that's 2 total meters. And that gives us a mu value of 0.0025. And then that's kilograms per meter. Okay. So if we plug those things in to our equation, we're going to have the square root of 1.962, all right, newtons over 0.0025 kilograms per meter. All right, and that works out to be 28.01 meters per second. Now, if you get a number like that, you might kind of be like, oh, wait a minute. The last one we did had a phase speed of 340 meters per second. This is a lot less than that. But that's okay, because the first one was in air. It was the speed of sound. Okay, this is just a vibration on a string, and there's no set number for what that's going to be. It's always going to depend on whatever tension, whatever mass. But it is almost certainly going to be way less than the speed of sound. Okay, so if you get a smaller number, it's not a big deal. It doesn't mean you did something wrong necessarily. Okay. Well, let's take those values and plug them back in for F3 because we got everything we need now. Okay, our velocity, 28.01 meters per second. Our wavelength, 1 meter. Okay, and so my meters cancels out, and I'm going to be left with, oh, look at that, 28 hertz. There we go. And again, you know, the last frequency we had was over 400. This one's super tiny. All right. The fact that it's so different doesn't mean you did it wrong. Okay. It's just the speed of sound is really high. Okay. Speed of sound is really high. Now, this string and this particular mass, that's something we could do in the lab. Okay. We could reproduce this in the lab easy. Okay. And these are all happen to be very realistic numbers. Okay. So there you go. Now, one more thing to think about. Okay. So I want you to sort of expand your mind a little bit, is that we could go in all different directions, right? It could be like, given the frequency and given the wavelength, how much mass do we have to have down there? Right? Or we might say, given the mass of the hanging weight, what's the mass of the string? Okay, so there's a whole bunch of different ways we could go with this. Find the wavelength, find the mass of the string, find the mass of the hanging weight, find blah, 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 blah. Okay, there's a lot of different ways we could go. But like I said in the last example, if you really commit yourself to understanding this and all the nuances here, you'll be in great shape, because there aren't actually an infinite number of ways to approach this or to deal with this. So, you know, what you're seeing here is going to cover you pretty good. You get your head around this, you're going to be in great shape. Okay. All righty. There you go. Hopefully that helps you out. Wrong lever.